Hey guys, so in this video, we're going to discuss Leetcode 1891. So where we're going to be given an integer array of ribbons where every item in the array represents the length of the ribbon. And we're going to also be given an integer k where we want to get k segments of the same length. So we can cut the ribbons into segments and we want to get the segments of the same length. And what we're gonna return is we're gonna return the segment, maximum length of the segments we can get. So for example, if the input is like 975 and the k is 3, which means we want to get 3 segments of the same length. So the maximum segment length we can get is 5, where we can get 5 from here. By cutting 9 into 5 and 4, we can get 1, 5. And cutting 7 here into 5 and 2, we can get another 5. And then we can get this 5 here, so we can get 3 5s. And another example is 759 and the k is 4. So we want to get 4 segments with the same length. So the output we can get is 4. So where we can get a segment of 4 from the 7 here, and another segment of 4 from the 5 here, and the 2 segments of 4 from the 9 here. So we can get 4 segments of length 4. So the naive approach to solve this problem is to just try out all the possibilities. Like we can starting from the length of 1, which is the minimum length of the segment, and then to see if we can get k segments of length 1 or not. If not, we just return 0, which means like it's not possible. Or if it's possible, then we can try 2, length of 2, to see if we can get k segments of length 2 or not until we fail. So we can just loop from 1 to 2 to 3 to 4 until we fail. Then the maximum number we can get is the maximum length of the segment we can get by cutting the ribbons. An optimized solution by solving this is using binary search. So what we can do is like we can define the lowest segment length is 1, and then the longest segment length is maybe like the total length of all the ribbons divided by k, which is the maximum length of the segments. And we can do a binary search from the lower number to the higher number. And for each mid number, for each binary search, we can just try the mid number, like which is the average of the low and the high, to see if for the mid number we can get k segments or not. If not, we can just update the higher bound to the mid number minus 1. Or if we can get the k segments for the mid number, then we can update the lower bound to mid plus 1. So let's loop through this example to see how it goes. So let's say if the input is 9, 7, 5, and the k is 3. So we can know the lower bound is 1. We can initialize the lower bound to 1 and initialize the high bound to 7, which is the total sum of the ribbons divided by 3, and which is the maximum segment length we can get. And the mid value would be 1 plus 7 divided by 2, which is 4. So let's say, can we get 3 ribbons with length of 4? Yes, because we can get 4 here, 2 4s from 9, 1 4 from 7. So we can get 4 ribbons from here. Now we can, if we can get, so we can know 4 is a valid answer. So we can try another, update the lower bound to 5, and the higher bound remain the same. So let's try to binary search on this end, and the mid number is 6, to see if we can get 3 ribbons of length 6. So we can get 1 6 from here, 1 6 from here, and no 6 from there. So we can only get 2 ribbons of length 6. So which means we cannot get 3 ribbons of length 6. So then we can update the binary search. So have the lower bound remain the same, which is 5, and the higher bound updated it to be a mid number minus 1, which is 5, and then the mid will be 5 plus 5 divided by 2. So can we get 3 ribbons of length 5? So which is yes, we can get 5 from here, 5 from here, and 5 from here. So now we can, which is valid. So we can continue binary search until we break out the binary search, which is like we keep on looping. So the lower bound will be mid plus 1, which is 6, and the higher bound is 5, so which we break out the loop because the lower bound is now higher than the higher bound, so which is like invalid. So now we just return the minimum value of the low and the high, which we break from there. So which is the valid answer of how many the maximum length of the ribbon segments we can get. All right, so basically this is the algorithm we're gonna use to solve the problem, which is binary search, and let's try to code it out. So first of all, I'm gonna get to the lower bound and the higher bound. So let's have the total equals to the sum of the ribbons, and the higher bound would be the total divided by k, and the lower bound would be 1. So there is an edge case here. So if high bound equal to 0, which means like we cannot get even segments of length ones, we just return 0. Now, while low is less than or equal to high, which is a binary search algorithm, so the mid value would be low plus high divided by 2. Now we can just try out to get k segments of length mid. So let's say segments would initialize it to 0. So for ribbon in ribbons, segments would equal to divided by mid. If segments is larger than or equal to k, which means like we can get k segments of this length mid, so we can try update the binary search to have the lower bound equal to mid plus 1. Else, which means we cannot get segments of k segments of length mid, so we can just update the high equals to mid minus 1. And in the end, we just return the minimum of mid and high. Mid and high, low and high, sorry. Let's try to run and see. Yeah, looks good. So for this algorithm, the space complexity would be like constant because we don't use extra space. For the time complexity, we should be log n, where n is the sum of all the total length of the ribbon. All right, so this is the end of the video, and I'll see you guys in the next one.